Hi, I'm Kuba and welcome back to Bielik Anatomy. So in the last episode we built matrix multiplication from scratch and we beat PyTorch for some matrix sizes. Now it's time for the other operations in the Bielik model like RMSNorm and Softmax. Individually they seem cheap, but they have a completely different performance bottleneck than Matmul. And to beat that bottleneck, we are going to fuse them. Modern GPUs have insane computer power. My RTX 4060 can do over 22 teraflops. It can process data incredibly fast. But every piece of data has to travel from memory first, and memory simply can't keep up, so the cores go idle. Almost 98% of the time, for an operation like RMSNorm, the GPU is doing nothing, just waiting for the next chunk of data to arrive. This is the memory wall, and it changes how you think about optimization completely. So here is a key insight. When we run RMSNorm as separate operations, square, mean, square root, divide, multiply, each of those is a separate GPU kernel. And each kernel has to read data from global memory, do its tiny computation, and write results back. The next kernel reads those results and does another tiny computation, writes back again. 5 operations, 5 round trips to slow global memory. That's the bottleneck. What if we could do all 5 operations in one kernel? Read the data once, do all the math while it's in the fast registers, write the final result once. 1 round trip instead of 5. That's kernel fusion, and it's basically the single most important optimization technique for memory-bound operation on GPUs. Let me walk through our RMSNorm kernel code step by step. The whole thing ran as a single GPU kernel, one program per row of the input tensor, and the beauty of it is a single pass. The first thing you will notice is how the kernel identifies which row it's responsible for. Each GPU thread block gets a unique program ID, its row index. We then advance the input and output pointers to point at the specific row using stride arithmetic. Every row processes in parallel. Next, we set up column indices and a safety mask. Block size is always a power of 2. We use 2048 for Bielik's hidden size of 1536. The mask ensures we don't read beyond the actual data when the block is bigger than the column count. Now the critical part, the one read from global memory. 2 vectorized loads, input row and weights. After this, everything lives in fast on-chip registers. No more global memory traffic until the very end. While the data is in registers, we compute the full RMSNorm formula. The epsilon prevents division by 0 when inputs are very small. Finally, the one write back to global memory. That's the whole kernel. One read, compute everything in registers, one write. Now for the benchmarks. First we'll compare our fused kernel against PyTorch's unfused path, which launches 4 or 5 separate kernels, each doing a slow round trip to global memory. Then we'll test it against PyTorch's native fused RMSNorm. To run these tests, I used Triton's native utilities. We ran 2 sweeps, one varying the hidden size and another varying the batch size, or number of rows. Let's look at the numbers. Our Triton kernel hits around 230 GB per second, saturating over 80% of my RTX maximum memory bandwidth. The unfused version peaks at just 150 GB per second. Why? because every intermediate step forces a slow round trip to global VRAM instead of staying in fast SRAM. Notice what happens at larger batch sizes. Our simple Triton kernel actually overtakes PyTorch's highly optimized native implementation. Finally, look at the compute. We are pushing a fraction of a single teraflops on a 22 teraflops GPU. The math is free. This operation is 100 memory bound, which is exactly why fusion is mandatory. Standard softmax needs 3 slow trips to global memory, finding the max, computing exponentials, and dividing them by the sum. We are going to do all of that in just one single pass. We are also making it causal. During the inference prefill phase, when we process the entire prompt in parallel, tokens are allowed only to look at the past, never the future. We bake this mask directly into the kernel. Let me walk through the code step by step. Step 1. Figure out which row and which position we are. Step 2. Load the entire row in one shot. Step 3. Apply the causal mask. Any column index greater than our current position is set to negative infinity. Since expo of negative infinity is 0, those future tokens get 0 attention weights automatically. Step 4. The numerically stable softmax. All in registers since the data is already loaded. And finally, one write back. Time to benchmark our Causal softmax. Again, we are comparing 3 paths: PyTorch unfused, PyTorch natively fused, and our custom Triton kernel. Just like before, I used Triton's built-in benchmarking tools to run sweeps across different head counts and sequence lengths. Let's look at the sequence length sweep, and this is where things get really interesting. Our Triton kernel scales flawlessly, capping out around 250 GB per second. But look at the PyTorch's native softmax. It peaks early and then completely collapses down to just 99 GB per second at a 4K context window. Why does it choke? Because explicitly adding a causal mask in standard PyTorch creates a massive temporary matrix in slow VRAM which destroys cache efficiency. Our one-pass Triton kernel applies this mask directly on the fly inside the ultra-fast SRAM. The result? At 1024 tokens, our custom kernel is literally twice as fast as native PyTorch. And just like before, with a peak of only 0.15 teraflops, it proves softmax is entirely memory bound. Fusing the causal mask isn't just a nice bonus, it's absolutely critical for long contexts. So what did we learn? The memory wall is real. For operations like RMSNorm and Softmax, compute is cheap, but memory access is expensive. Kernel fusion is the answer, combining operations to minimize memory round trips. The takeaway is simple. When we are memory bound, don't optimize the compute. Optimize the data movement. Fuse everything you can. If you are following along, the code is on GitHub. Thanks for watching. Next episode we are tackling rope, rotary position embeddings. That's how BIELIK encodes where each token is in the sequence. Should be interesting. See you then.